The evolution and diversity of machine learning algorithms in modern computing in recent years, machine learning has emerged as a cornerstone of technological innovation across industries ranging from healthcare to finance. The ability of algorithms to learn patterns from data without explicit programming has revolutionized how we approach problem solving in complex domains. This article delves into the intricate world of machine learning algorithms, exploring their classification, functionality, and practical applications. We'll examine both traditional models and cutting-edge advancements shaping today's AI landscape. Fundamental concepts behind machine learning algorithms. At its core, machine learning involves training algorithms to make predictions or decisions based on input data. This process typically requires labeled datasets where each example contains known outcomes. The primary goal is to develop models that can generalize well beyond the training data. Effective generalization ensures accurate performance when applied to new, unseen information. Three key components define any machine learning system: features, input variables, labels, output targets, and the model itself, which learns relationships between them through iterative optimization. Different types of problems require distinct approaches. Regression tasks predict continuous values, while classification identifies discrete categories within data samples. Classification algorithms. Making predictions with precision. Classification algorithms are essential tools for categorizing data points into predefined classes. These algorithms excel at identifying patterns that distinguish different groups within dataset samples. Commonly used techniques include logistic regression, decision trees, random forests, support vector machines, SVMs, and neural networks. Each method offers unique advantages depending on the nature of the task. Logistic regression provides probabilistic outputs by fitting data to sigmoid functions. Decision trees create hierarchical structures that split data based on feature thresholds. Random forests enhance accuracy through ensemble methods that combine multiple decision tree models. Support vector machines find optimal hyperplanes that maximize separation margins between classes. Logistic regression, simple yet powerful for binary classification tasks involving linear separability. Decision trees, easy to interpret but prone to overfitting unless properly pruned. Support vector machines, effective for high-dimensional spaces with clear margin boundaries. Neural networks, capable of capturing non-linear relationships through layered architectures. Regression techniques. Modeling continuous relationships. Regression analysis focuses on predicting numerical values rather than classifying categorical outcomes. Linear regression remains the most fundamental technique for establishing such relationships. Linear regression fits best fit lines through scatter plots using least squares optimization. More advanced variants handle nonlinearity through polynomial expansions and regularization terms. Lasso and ridge regressions introduce penalties during coefficient estimation to prevent overfitting issues common in high-dimensional datasets. Elastic net combines L1 and L2 regularization strategies, offering flexibility between sparsity constraints and stability requirements. Tree-based regression models like random forest regressors and gradient boosting provide robust alternatives particularly useful for noisy real-world data. Unsupervised learning methods, discovering hidden structures. Unlike supervised approaches requiring labeled examples, unsupervised learning works exclusively with unlabeled datasets. Clustering algorithms form natural groupings based on similarity metrics. K-means clustering partitions observations into K-clusters, minimizing intergroup distances while maximizing intercluster differences. Hierarchical clustering creates nested cluster formations representing various levels of granularity. Principal component analysis. PCA reduces dimensionality by transforming correlated features into orthogonal principal components. Autoencoders serve as deep learning counterparts, implementing nonlinear dimension reduction through encoded representations learned via backpropagation. Ensemble learning strategies, combining weak learners into strong models. Ensemble methods aggregate predictions from multiple individual learners to achieve superior overall performance. Bagging, boosting, and stacking represent three dominant paradigms in this space. Bagging improves variance reduction by averaging results from bootstrap samples taken repeatedly from original datasets. Random forests exemplify this principle using diverse decision trees trained independently. Boosting sequentially trains weak classifiers, focusing more attention on misclassified instances until satisfactory accuracy levels are achieved. AdaBoost and XGBoost are popular implementations demonstrating effectiveness across numerous benchmark problems. Deep learning architectures. Advancing neural network capabilities. Deep learning leverages multi-layered artificial neural networks capable of modeling highly complex functional mappings. Convolutional neural networks, CNNs, excel at processing grid-like data structures such as images. Recurrent neural networks, RNNs, maintain memory states, making them suitable for sequential prediction tasks including language translation and time series forecasting. Transformers utilize self-attention mechanisms, enabling parallel computation capabilities crucial for handling long-range dependencies effectively. GANs, generative adversarial networks, consist of competing generative and discriminative models driving innovation in synthetic data generation and style transfer applications. Beyond traditional approaches, emerging trends in algorithm development. Current research explores novel directions, expanding conventional algorithmic frameworks. Reinforcement learning enables agents to learn optimal behaviors through interaction with environments. Federated learning addresses privacy concerns, allowing collaborative model training across distributed devices without sharing raw data directly. Explainable AI initiatives aim to increase transparency surrounding black box models, promoting trustworthiness among end users and regulatory bodies alike. Quantum computing presents exciting possibilities, although widespread adoption remains several years away due primarily to hardware limitations currently facing quantum processors. Performance evaluation metrics for algorithm selection. Selecting appropriate evaluation criteria plays a critical role in comparing different machine learning solutions objectively. Accuracy measures proportion correctly classified instances but may be misleading under imbalanced conditions. Precision focuses on positive predictive value, assessing how many true positives exist relative to total predicted positives. Recall quantifies fraction of actual positives identified correctly out of all existing ones. F1 score balances precision and recall, providing harmonic mean measure, especially useful when dealing with skewed distributions commonly found in medical diagnostics scenarios. AUCROC curves plot trade-offs between false positive rates against true positive rates, varying threshold probabilities, helping visualize classifier performance comprehensively. Practical considerations when implementing ML solutions. Successful deployment hinges upon meticulous pre-processing steps, ensuring quality inputs reach modeling stages intact. Data cleaning removes inconsistencies, improving reliability downstream processes. Feature engineering transforms raw attributes into meaningful representations, enhancing model interpretability and predictive power significantly. Domain knowledge guides effective transformation choices wisely. Cross-validation techniques validate model robustness, preventing overfitting tendencies often observed during initial development phases. K-fold cross-validation splits dataset into K segments, iteratively testing each partition. Hyperparameter tuning optimizes configuration settings, influencing final output characteristics substantially. Grid search exhaustively evaluates combinations systematically, though computationally intensive. Conclusion: making informed decisions about algorithm selection demands understanding strengths, weaknesses associated with particular methodologies suited towards specific application contexts. Continuing education stays vital amidst rapid advancements, continuously reshaping our field's technical landscape, keeping practitioners updated regarding latest breakthroughs available today.